You know, when it comes to digital security, having a strong lock is only ever half the battle. Seriously, it's the strategy, how you actually use that lock, that makes all the difference. It's what separates a real fortress from, I don't know, a flimsy screen door. And today, we're going to dig into those strategies.
So here's the big puzzle we're going to try and solve today. Imagine this. How do you secure an entire email with a lock that can only fit on a single word? It sounds kind of weird, right? But that's the thing. We have these amazingly powerful encryption tools, but they're built to work on these tiny little fixed-size chunks of data. So the real question is, how do we take that and scale it up to protect, whole messages, entire files, or even our hard drives?
Okay, so the main tool for this job is something called a block cipher. And really, all it is an algorithm that grabs a fixed size piece of your data, let's say 16 bytes, for example, and just completely scrambles it using a secret key. You can think of it like a super secure digital padlock for one tiny, standard-sized box. It's amazing for that one box, but what about all the other boxes? And that right there, that brings us to the core problem that cryptographers had to crack. How in the world do you securely use a tool that's designed for one tiny piece of data to protect something absolutely massive? This is what's known as the one block problem. I mean, think about it. You can't just encrypt the first 16 bytes of a huge movie file and say, yep, we're secure, right? No way. You need a repeatable and, more importantly, a secure method for using that tiny lock again and again and again. And this is where the real strategy kicks in. These methods, they're called modes of operation. And honestly, they're the secret sauce behind almost all modern encryption. So what's the first thing that comes to mind? The most obvious way to solve this? Well, you'd probably think, hey, let's just chop the data into blocks and encrypt each one by one. And you'd be right. That's exactly what people tried first. The problem is, it's also incredibly dangerous. This first attempt is called electronic code book mode, or ECB for short. And the logic seems super simple, right? You just slice up your message into those standard-sized blocks, and then you encrypt every single one of them individually with the exact same key. Seems pretty straightforward. So you can see the process is totally parallel. Encrypting one block has absolutely zero effect on any other block. They're all done in their own little isolated worlds. And while, yeah, that's fantastic for speed, it creates a massive fundamental security flaw. And here it is, the fatal flaw. Because you're using the exact same key on every single block, if you have two blocks of original data that are identical, well, you're going to get two blocks of encrypted data that are also identical. The encryption is what we call deterministic. So what does that really mean? It means all the patterns, all the repetitions, all the underlying structure from your original file, it just leaks right through into the encrypted version. And this next part, oh man, it illustrates just how bad that can be. Okay, look at this. On the left, we've got a normal, unencrypted picture of a penguin. Now look at the right. That's the same exact image after it's been encrypted with ECB. You can't see the fine details, sure, but you can absolutely 100% still see the penguin. So why is that? It's because every single block of white pixels was encrypted into the exact same ciphertext block, and every block of black pixels did the same thing. You've hidden the content, maybe, but you have not hidden the structure. And trust me, this is not just some theoretical what-if problem. Think about a bank transfer that's encrypted using ECB. An attacker could intercept it and figure out which encrypted block corresponds to their own account number. And once they have that, they can just copy and paste that encrypted block into other people's transfers, redirecting all that money to themselves without ever needing the key. That's a huge deal. So, yeah, clearly ECB is a total disaster, which is why cryptographers came up with much smarter strategies. Strategies that involve things like chaining blocks together and creating these wonderfully unpredictable streams of encrypted data. All right, so the first big improvement we're going to look at is called cipher block chaining, or CBC. And the name pretty much gives the game away, right? The blocks aren't independent anymore. They're chained together. So here's how CBC completely fixes that big problem with ECB. Before any block gets encrypted, it first gets mixed together with the encrypted result of the block that came right before it. See, it creates this chain of dependency. And what that means is, even if you have two identical blocks of plain text, say 2 blocks of all white pixels, they're going to encrypt as something totally different because the encrypted blocks that came before them were different. And to get the whole thing started, the process is kicked off with a random starting block. We call it an initialization vector, or an IV. And that little thing is what guarantees that even if you encrypt the exact same message twice, the final result will look completely different each time.
Now, there's another really brilliant approach called counter mode, or CTR, and this one kind of flips the whole script. Instead of encrypting your data directly, what you do is you encrypt a simple counter, just the numbers 1, 2, 3, 4, and so on. This creates a totally unique and unpredictable stream of data. Then you just mix that stream with your actual message to get the final ciphertext. It's so cool, it basically turns our blocky, one box at a time lock into a continuous, flowing stream of encryption.
And the huge advantage here? Speed. I mean, massive speed. Because encrypting, say, block number 100 only depends on the number 100, not on what happened with block 99. You can encrypt all the blocks at the same time. You can just process them all in parallel. And that's what makes CTR mode absolutely perfect for stuff that needs crazy high throughput, like streaming video or securing high-speed network traffic. But these days, good encryption has to do more than just hide your data. It needs to be able to fight back, especially against tampering.
And that brings us to what is basically the modern gold standard, Galaz/counter mode, or GCM. What it does is it takes all that high-speed parallel goodness from counter mode and then adds this incredibly powerful layer of protection right on top.
GCM gives you something called authenticated encryption. And that means it doesn't just give you confidentiality, the promise that your message is secret. It also guarantees two other crucial things, authenticity and integrity. So what does that mean for you? It means you can be absolutely sure the message is really from who it says it's from, and that not a single bit was changed or messed with while it was on its way to you. It's this whole security package that makes GCM a cornerstone of the modern internet. It's used in things like the HTTPS that's securing your browser connection right now.
Okay, so we've got all these amazing, powerful strategies, but at the end of the day, they all rely on the underlying block cipher, the basic lock, being strong. So what happens when that foundational lock starts to get a little old? Like the once mighty DES algorithm. Can you actually make an old lock stronger without just throwing it out and getting a new one?
Well, the first idea you'd probably have is, hey, let's just encrypt the data twice with two different keys. You'd think that would, square the security, right? Make it way stronger. But it turns out there's a really clever technique called the meet-in-the-middle attack that just breaks this wide open. It works by attacking the problem from both ends at once, from the original plaintext and the final ciphertext, and looking for a match, a collision, somewhere in the middle. And the result is pretty shocking. Double encryption is barely any more secure than just encrypting at once.
The real solution that people landed on was triple encryption, specifically a version called triple DES, or 3DES. And it uses this kind of counterintuitive encrypt, decrypt, encrypt sequence. This clever little pattern is what makes it resistant to that meet-in-the-middle attack. And man, this thing became the workhorse of banking and enterprise security for literally decades. Now, here's a fun fact. Even though triple DES uses 3 56-bit keys, the actual security you get isn't 3 times 56. Because of the way the attacks against it work, it really just doubles the original key strength. So that gives it a really solid security level of 112 bits.
And all this really brings us to the final big takeaway. From the absolute train wreck that is ECB, all the way to the incredible protection of GCM, we've seen over and over that the encryption algorithm itself is only half the story. It's the strategy, the mode of operation. That's what actually turns a simple lock into a real fortress. And it forces us to ask a really important question about our own digital lives. Are we just focused on having strong passwords, the lock? Or are we also thinking about the strategy of how and where we use them? Because that is the difference that truly matters.